Good morning and welcome everyone to another Athena talk and Hellenic Mediterranean University Sci Cafe talk. It's a great pleasure for us and a great honor actually to have today Dr. Chrysanu Day, a friend from the past, from me, during our common time in the UK, when I have my postdoc research in the University of Cambridge. So a short introduction about Chris, and then I will give him the floor for his very interesting presentation, I'm pretty sure. So Chris is currently a postdoctoral researcher at the University of Oxford in the United Kingdom, and he's working on perovskite solar cells and other optoelectronic applications in the group of Professor Henry Snaith at Clarendon Laboratory at the University of Oxford. He also serves as a stipendiary lecturer in one of the colleges, Trinity College of the University of Oxford, and also he is a junior research fellow at Worcester College, which is a very big accomplishment for every postdoc to become a research fellow in this type of university. And before this appointment, he was also uh, researching perovskite-based materials and applications on the basis of a PhD at the group of Professor Sam Strangs in the physics department of the Cambridge University and the Cavendish Laboratory, a very historic laboratory of the University of Cambridge in the UK. And prior to this, he also was a master student and a bachelor student at NUS, National University of Singapore, and he worked towards the application of metal oxide semiconductors as transparent electrodes for optoelectronic applications. Chris also has received several fellowships and several awards, including a Cambridge Indian Scholarship, a Cambridge Philosophical Society Research Studentship, and also an EMRS Graduate Student Award. So, Chris, it's a great pleasure and honor to have you today, and we are really looking forward to your presentation. Please share your screen, and you have approximately 45 minutes. Thanks a lot.
Thank you very much, George, for the very kind introduction and for giving me the opportunity to share some of the work I've done in the last few years. Can I just check you're able to see my screen well and hear me well?
Yes, it's very.
Yes. Okay. Great. So yeah, hello everyone. George has said almost everything about me, but yeah, so I'm a postdoc at Oxford, and today I'm going to talk to you about mixed metal halide perovskites in general, and specifically looking at their bright aspects. And I'll tell you in a short bit why I mentioned the bright aspects in the title. So, I mean, George already said this, but I just thought I'll just show you where I come from, because I guess the audience here consists of people from diverse geographical locations. So I come from India, in the northeastern part of India, the state of Assam, which is known for its tea. And my town that I come from, it's a very small border town called Sribhumi. It borders Bangladesh. And so you can see it's very far from Delhi, Mumbai, and other metro cities in India. So come from very far. So close to my hometown, I did my undergrad in engineering, electronics and communication engineering in NIT Silchar. And then I moved to NUS Singapore for my MEng, and then I changed my field from engineering to physics when I came to Cambridge for my PhD, and now I'm continuing that in Oxford. My research area currently is on perovskite LEDs, mostly looking at both the three-dimensional perovskite, lower dimensional perovskites, and their heterostructures. But I'm not going to talk about those today. Instead, I'm going to talk about what I did in my PhD on mixed lectin halide perovskites. So this is the brief content. So I'm going to start with some idea about why mixed lepton perovskites are important, and then present some of the results in the 4 sections, and then conclude with a brief summary. So as I have seen, the Athena talks cover a broad variety of topics. So I guess it's good for me to give you a brief introduction about what perovskite is. So halide perovskites are a class of materials with the general formula of ABX3. Let me just try to, sorry. Let me just try to get my laser pointer. So yeah, structure like this with the formula of ABX3. And these were discovered a long time ago, but only in 2009, the group of Tom Miyasaka in Japan, they found that these materials can be pretty good solar absorbers. And then since then, over the last 15 years, the efficiency of these materials have grown up significantly. This is some of the uh, data that I made like a couple of years ago. Some of the data points are now obsolete. The perovskite single junction efficiencies are now close to 27%, whereas the perovskite silicon tandem is now close to 34%. So it's increasing in an unprecedented manner. And so this has been a really great decade for perovskites. But again, not everything is great for these materials. These are soft semiconductors. So that means the constituent ions are mobile and they can respond to external stimuli. And this constitutes a problem of the stability of these materials. So yeah, as I said, this is the current status. The tandem efficiencies are rising at an unprecedented rate, and they're making tandems with all kinds of materials, with silicon, CIGS, or with other kinds of perovskite as well. And this is where this kind of research comes in. So if you want to stack 2 different perovskites with a higher band gap and a lower band gap, and you want to get the highest efficiencies, this is a paper that shows that what efficiency maximum you can reach if you choose the right combination of band gaps. And you can see that basically you need to have some band gap for the lower band gap perovskite needs to have a band gap about 1.2 electron volt or close to that. And unfortunately, the traditional lead-based perovskites cannot reach that band gap, and which is why we need to alloy lead with tin and makes this mixed metal composition to reach that band gap, which are then useful for all perovskite tandem applications. Now, these perovskites containing tin have some problems, and it's been known for several years now, and it comes from the basic chemistry. As you would already know, that the tin, because of the because of the lone pair effect, they want to be in the +4 oxidation state, whereas in the perovskite structure, they are forced to be in +2 oxidation state. So as soon as they see some oxygen or they're exposed to air, they tend to oxidize pretty quickly, and there are different ways of degradation of these materials, and that are like already discussed quite extensively in the literature. These publications talk about them, and when they degrade, they also affect the optoelectronic properties of these materials. So it's very hard to work with these materials if you can't control the conditions of your glove box, let's say, and your measurement right. So this is all the problems that people already know about tin-based perovskites, but they have some interesting properties, some of which I already mentioned today. But we wrote a perspective article during the COVID period. So if you want to know more about these materials and what they can do and how they are different from the traditional lead-based perovskites, you can refer to this paper. But with that, let me just jump straight into the results section. So in my research, I did not want to look at just chasing efficiencies. Instead, I wanted to look more into the fundamentals of these materials. So one of the things that I started to look in the beginning was the charge transport in perovskites, and you know there are different ways of measuring charge transport in semiconductors. Some of those are optical-based techniques like terahertz spectroscopy, but some of those are also electrical-based long-range methods like SCLC or Hall measurements. And this is where I tended to use this other technique, which is the field effect transistor technique. And why I use that is because it can give you information about long range transport, which is important for solar cells, LEDs, or any other kinds of devices where the charges need to travel to longer distances, it can easily tell you whether the transport is happening from the holes or the electrons, so it's sensitive to polarity of the charges. It can also probe the ion migration. As I mentioned, it's a very big challenge in the field of perovskite, so this kind of technique can also give you some idea about ion migration. And for all these things, these are relevant for devices. So in my research, this is the configuration of field effect transistor I used. So it's a 3-terminal device with a gate source and a drain electrode. The transport happens between the source and drain electrode, and you build the channel on a conducting path for carriers by applying a voltage at the gate terminal. So that's how it works. These are the materials that I used for the different layers. So the perovskite semiconductor is what forms the channel material, and I deposited the last step of the fabrication. So just in case people are not aware about how the FET characteristics look like, so just like solar cells, they also have JV characteristics, but because these are 3-terminal devices, so they will have 2 kinds of JV characteristics. One looking at the drain source current, which is the main channel current, as a function of the drain source voltage, and another characteristics is the drain source current as a function of gate source voltage. So you call this particular drain versus drain current, drain voltage characteristic as the output characteristics, and you call this drain current gate voltage characteristic as the transfer characteristics. And using all these different equations that are taught to a lot of undergrads in engineering or physics, you can basically calculate the mobility, which is the most important characteristics of a transistor, and lots of other things, including subthreshold swing, threshold voltage, on-off ratio, and things like that. So this is what I started to do. So I start to go from pure lead perovskite and then to pure tin, or at least tried to go there. So what happened is that if you look at the pure lead perovskite, this is how the transport looks like. So you can see that the current increases when the gate voltage goes to the positive axis. So when the gate voltage is positive, you are basically inducing a lot of electronic carriers to come to the surface or like interface with the dielectric we call the channel. So that means this increase in the current is driven mostly by the electrons, and that's why you call it the n-type transport. And we found that the maximum mobility is about 10 to the power minus 3 centimeters square per volt second. But this trend completely reverses when you use some bit of tin in there. So you now see that the current increases when you are going mostly in the negative voltage regime. So that means you are inducing the oppositely charged holes now in the channel. So it's a p-type transport now. So the thing that we see that introducing tin changes the polarity of your transport, so it makes it hole transport predominantly, and the mobility also increases steadily. The maximum mobility we can reach is 5.4 centimeters square per volt second, with very little hysteresis in the output characteristics, and I'll talk about that in a little bit more detail later. And this kind of numbers are still highest for this kind of compositions. And then we try to go to even higher tin content. So this is for 50-50 lead tin. If we go to higher tin, we can see that the JV characteristics or the transfer characteristics looks flat. So that means the current is not changing with the gate voltage, and this happens when the channel is already full of charge carriers, or when the channel is very much doped. So it acts like a semi-metallic semiconductor, which is not really good for a transistor, which is why you don't really see any gate modulation of the current. Anyway, so we did some theory calculations with some of our collaborators, and we found that including some tin in this adds some additional density of states in the valence band maximum, which can basically explain why you are getting a predominant p-type transport in the presence of tin. And when you do some band structure calculations, you find that the curvature of your valence band maximum increases with tin, and we know that the curvature is related to the effective mass. So stronger the curvature, lower the effective mass, and this is what we also see that the decreasing trend as you introduce more and more tin. And then we look at the surface morphology using SEM, and we also find that increasing the tin increases the grain size or average grain size of our films, and this is in agreement with the obtained mobility trend. And then we wanted to understand how the charge transport happened, and if there is any influence of mobile ions in these devices. So the reason for trying to look into that was the 3D perovskite FETs have been worked on for many for at least a couple of decades now. That they have a problem is that when you are applying a voltage at the gate terminal, and you are trying to induce, let's say, negatively charged electrons, because the iodide ions are also mobile, they can also get attracted towards the interface. So those ions can then also shield some of those applied voltage and screen some of that from getting applied on the electrons, let's say. And that is why the effective voltage that is applied on the channel is far reduced. And therefore, as you go to higher and higher temperature where ions can move much faster, you reduce the mobility. That's a trend that's been seen in many papers. So the mobility decreases as you go to higher temperature, and this is believed to be due to the ion migration or the ionic screening effects. So I wanted to see whether this effect still is predominant in the tin-containing perovskite devices. So we did the same measurements starting with the pure lead, and you can see for the pure lead we see a very similar trend. So the reduction of the mobility measured from the FET as a function of temperature, so it goes down, and this is a characteristic of an ionic screening behavior. But as soon as you introduce something in there, you again completely change the behavior. You now see a positive temperature coefficient or an activated behavior. And if you uh, do a kind of a fitting of that positive increase part of the curve with the Arrhenius equation, you can find the activation energy, and we can find that our best composition, which is the 50-50 lead tin composition, has a pretty low activation energy, suggesting presence of shallow defects. And looking at the literature, we know that these tin-containing perovskites contain a great amount of tin vacancies, which are believed to be shallow. So this might be a way of seeing that in our temperature-dependent measurements. Now, this was the first time we saw such behavior in any kind of 3D perovskites. And to understand that even more conclusively, we did some scan rate dependent measurements, which are known to be a pretty nice indicator of the ionic migration. So you can see at room temperature for the lead-based perovskites, as you change the scan rate from a higher scan rate to a lower scan rate, you are changing the hysteresis in these transfer curves. And then this change is basically suppressed as you go down to 200 and 100. So that tells you that this change in hysteresis is got to do something with temperature, and hence also with the motion of ions. And another way of understanding that is that the current that you see for the drain current that you see at higher scan rate reduces quite significantly as you go down to lower scan rates, and that's also because of some ionic screening. So if you give more time for the ions to move, they can screen better, and you will get lower and lower drain current. So both of these things show you that in the lead-based perovskites, the transport is very much affected by the ions. But if you look at the lead-tin perovskites, you see that there's very little change in the hysteresis at room temperature, which is great. And again, for the lower temperature, we expect them not to have any effect anyway. But more importantly, there is very little change in the drain current as you go down from higher scan rate to a lower scan rate. So again, both of these things are telling you that in the tin-containing perovskite devices, you have low ionic screening effects. And then we wanted to visualize that. So we made some two-terminal devices. So these are just not FETs, just two-terminal devices. And we measure the PL of these structures, and then we apply some voltage and then remeasure the PL. So this is how these measurements are done. So you can see for the lead-based perovskites, we initially start with a nice high PL in the channel region for perovskite. As you apply some voltage pulses and track the PL, you can see the PL starts to reduce, and it starts from one of the sides of the structure and then percolates throughout the channel region, and after several cycles of these pulse voltages, you get very low PL count. So this means that the ions are moving, creating a lot of defects, and therefore your photoluminescence efficiencies or photoluminescence intensities go down pretty significantly. And this is a well-known technique in the literature to probe ion migration in different compositions. So then we did the same measurements, but now for the mixed lead tin perovskites. And you can see that for the mixed lead tin perovskite, generally there is a little bit of change after the first cycle, but after that, the behavior is pretty much constant. So there is no further change that happens after the first biasing cycle. So it tells you that that ion migration behavior is definitely present, but it's certainly much slower or suppressed, let's say, than the lead-based perovskites. We see the same behavior for the mixed lead-tin perovskites. But there's an interesting thing that we see, that if you look at these negative electrode, we see that if when we are biasing the negative electrode for the tin-based perovskites, they tend to increase in intensity, which is not seen in the lead-based perovskites. So that was very interesting. So negative electrode has a lot of electrons, of course. So something is happening as you are biasing them, and we wanted to see whether this is reversible, and then we left them under the non-biased condition, and if we just let them relax and then we track the PL again, we see that they increase first, and then if you leave them unbiased, they go back to lower PL again. So seems to be happening something when you are applying the bias, and this is where we kind of propose a reversible electrochemical reaction where the tin 4 plus, which I said is always almost certainly present in these materials, get reduced to tin 2 plus in the presence of these electrons. And this tin 4 plus is known to be a big source of defects. So as you are reducing the defects in situ by these negative electrons, you are getting a higher and higher PL. But when you don't have that voltage, the tin doesn't want to be in that state, so it goes back to tin 4 plus, and therefore the PL decreases. So that's where we kind of come and propose the hypothesis. But long and short of the story is that what we find generally in these tin-based perovskites, the lateral ion migration is significantly suppressed as compared to the pure lead-based perovskites. And then we propose some mechanism why this could be happening. So one of the things that is already you might already notice is that in the case of lead-based perovskites, we had an N-type transport. So the ions that could have shielded the voltage are iodide ions, whereas in the case of the tin-based perovskites, because it's a P-type transport, so the migration of iodine is not very important, whereas the migration of the positively charged ions are more significant. But again, we know from literature that the positively charged ions tend to move slower than the iodide ions. So that could be one of the things. But even if they move, we believe that because these tin-based perovskites have a lot of these tin vacancies, as I mentioned, these tin vacancies can easily ionize to give rise to holes. So then they are left with these negatively charged acceptor ions, which can form a neutral defect complex with these ions, A plus or B2 plus. As a result, you certainly form some kind of a neutral defect complex which cannot shield the electric field anymore. So that is the two mechanism for an FET structure, but you also see that even in an in-plane device without a gate, we see that there is a suppression of the ionic migration in the tin-based perovskites. Next, we wanted to see whether this kind of behavior is specific to field effect transistor, or can we actually generalize them? So we do similar kinds of measurements now on an optoelectronic device, so some vertical structure device like solar cells. So we make some solar cells with a very similar composition. So it's a pure lead versus lead tin. Let's say we make some PIN solar cells with these compositions. I deliberately did not put any kind of passivation in these materials because we wanted to specifically look at the effect of tin. So we can see that we can obtain 15 to 16% without any passivation, which was decent at the time. And then specifically what we were more interested in was looking at doing the scan rate dependent measurements, so JV measurements. And we see that as you increase the scan rate, the current JSC increases for both of them, and something that's already known in the literature, that this kind of behavior indicates the motion of ions. So basically, it says you that the lead and lead tin both have ions that they can move. However, if you look at specifically that hysteresis behavior as a function of scan rate, what you see is that for the case of lead-based perovskite, the peak of the hysteresis, which basically tells you a little bit about the speed of the ion migration, will have a peak that will come sooner, much faster, let's say, as compared to this lead tin. So that means the peak scan rate of the lead hysteresis will be higher than the lead tin hysteresis. So that means that in the case of lead-based perovskites, we will possibly have a faster ion migration than in the case of lead tin. And to get some more conclusion on this behavior, we did some electrochemical impedance spectroscopy on full devices. These are done under open circuit conditions under one sun. And you can see for the lead-based perovskites, we see the classic two semicircle behavior from the Nyquist plot. And so this corresponds to a high frequency peak and a low frequency peak. The high frequency peak is generally attributed to non-radiative recombination generally, and the lower frequency behavior is attributed to processes which are happening at a longer time scale. One of those could be ion migration. So what we see for the lead-based perovskites, that as you increase the temperature from, let's say, 20 degrees to 40 degrees, that lower frequency peak kind of shifts to the right. So that means your ion migration is becoming faster with temperature, which is basically very much understandable because the ions will have more thermal energy to move. And so we are able to see that in the impedance spectra. However, in the case of lead tin, we only see one semicircle, meaning that only one high frequency peak. The low frequency peak, which is generally attributed to the high ion migration, is basically absent, even down to much lower frequencies than what I showed for the pure lead perovskite. So these kind of things tell you that in the case of lead tin-based perovskites, the ion migration is much more suppressed. Okay, so all these measurements kind of made us more confident to say that lead tin perovskites generally have slower ion migration, and we have shown this with FETs and solar cells both. And then to understand what is happening atomically, so we did some, so our collaborators did some ab initio DFT calculations. And what we find is that if you just, like, let's say, go from a pure lead system to a pure tin system, let's say go from Fe iodide to Fe tin iodide, we don't see a huge change in the ion migration barrier. So these are pretty similar. So this can't really explain why, in our case, in the case of tin-based perovskites, the ion migration is becoming so slower. But then we introduce some tin vacancies in the structure, and this seems to be the key. So this then increases the ion migration barrier significantly for both pure tin perovskites and mixed lead tin perovskites. So it tells you that if you have some vacancies in the structure, this will create some local distortion in the lattice, and that will inhibit the long range ion migration in these perovskites, which is where the ion migration barrier increases. And this kind of explains well what we saw experimentally in the last few slides. Okay, so this brings me to the final section, and this is something that's not published yet. So can I just request George to pause the recording if you can, and then I'll proceed with. Okay, so this is where I come to the conclusion. So what we showed to you is that some of the bright aspects, as I mentioned. What are the bright aspects? Of course, the first one, we showed to you that lead tin-based perovskites have a much higher hole mobility as compared to the electron mobility that you see in the pure lead-based perovskites. So these are pretty highly mobile semiconductor, which is really great. We also see that the temperature activated behavior in these materials, telling you that you can basically probe the shallow defects using these kind of measurements. We also see the ion migration in the in-plane direction is heavily suppressed in the lead-tin perovskites. We then also did the same measurements on a vertical architecture device like solar cells, and we also see a very similar effect that the ion migrations are mitigated in the presence of tin. And then we went far into halide segregation, and you also show that in the presence of tin, halide segregation is very much suppressed as well. So the long and short of all the stories that I've presented so far is that mixed lead-tin perovskites have a lot of advantages over pure lead-based perovskites. It's not always about the stability that people crib about, that, oh, these are very unstable, so why should we even work on them? I show you some avenues where they can be much, much better than pure lead-based perovskites. The key is, of course, always how do you explore those attributes. With this, I want to thank all the people that have supported me in this work, all the funding agencies, and finally to you all for your attention. If you have any questions, I'm very happy to take. And these are my contact details if you want to reach out to me later as well. Thank you very much.
Thanks a lot, Chris, for this very interesting and, let's say, non-conventional perovskite presentation, that you presented something different on this regard. So thanks a lot for the presentation and the interesting results. Congratulations on them. And now we have some time for Q&A. Okay, I can see Samuel with a hand raised. So would you like to unmute, please, and ask your question?
Yeah, you hear me?
Yes, yes.
Okay, thank you very much on the interesting presentation. And I want to ask you a question. How technologies of mixed Halide perovskites can support development low-cost technologies for transport and agriculture?
No, that's a very good question, and it's actually an emerging area, especially for transport. Let's say agriculture. I mean, it's kind of related, the transport and agriculture. But this area is very nascent still now. So what happens is that for the time being, all our transport, let's say, is happening with the fossil fuels, and which are known to be polluting, and they are not in abundance. So we want to move into renewable fuels, liquid fuels, hydrogen or ethanol, methanol, or any other kinds of these chemicals. So if you can process them using some kind of a renewable method, maybe solar, it'll be great. So perovskites are really good in that, because if you want to drive those reactions electrochemically, you need a pretty high voltage. And perovskite solar cells, especially in the tandem and multi-junction configurations, can give you that very high voltage. So if you are able to get those high voltages, you can drive those chemical reactions to produce hydrogen and ethanol and methanol and things like that. So if you're able to produce those chemicals which are used in the transport sector, this will pretty much be revolutionary. So you don't have to basically move away completely to EV. You can still use the general liquid fuel based is vehicles. It's just that those fuels will now be produced in a more let's say green fashion. Regarding agriculture, ammonia is one of the very important let's say ingredients for any fertilizers. So it's very hard to make ammonia. Currently, it's made by Haber-Bosch process, which is a very highly temperature process. So it's very highly energy intensive. If you are able to also make ammonia using electrochemical processes, and mind you, they need a very high voltage, about close to 4 volt or something. So if you are able to make, let's say, 4 junction perovskite solar cells that can give you 4 volt of open circuit voltage, you can ideally ideally drive such ammonia production as well. So again, these are all thoughts and something that I'm trying to explore for my next postdoc or even in my future group, whenever that happens, is the field of solar fuels and chemicals, where perovskites can really be very useful. But for the time being, it's not been done, but definitely they have a huge potential.
Thank you, Shmuel, for the question, and Chris for the response. And yes, please, George.
Yeah, thanks a lot for the presentation. Very nice stuff. I have two naive questions. First of all, in one of your first transparencies, you showed that the efficiency of photovoltaics goes up to 30 something percent, I believe now.
Yes, yes.
So is there any fundamental reason? Yeah,
You mean this one?
yeah.
Yeah.
Is there any fundamental reason which prohibits us from reaching, close to 100%, or is it,
Yes. Yes. Yeah. That's a very good question. Maybe I should have mentioned. So if you are having only one absorber, there is a limit called Shockley-Queisser limit. So that's a thermodynamic limit that kind of prohibits a single junction or like one semiconductor based solar cell to only give you a maximum of 33%. Why it's not 100%? Because you are losing a lot of these you're also having a lot of other losses. Some of the losses could be like if you have a semiconductor with a certain band gap, you can only absorb photons which have an energy higher than the band gap. All the other photons below the band gap will be transmitted, so they're not absorbed. So that's one of the photonic losses.
Yeah.
Another thing is like if you're let's say absorbing a photon which is a very high energy, so you are exciting your electrons from the valence band to very high in the conduction band. They don't want to be in that very high energy state. They want to relax and come down to the conduction band minimum. So you're losing that extra energy also. We call it thermalization. So thermalization losses, then this transmission losses, and of course then there are also defects in perovskite materials that you can't really probably avoid. So all these different scenarios kind of bring this maximum limit to below, much below 100%. Now for a single junction it's a 33% limit. For a two junction it's close to 40 or 42%. For a three junction it's a bit higher. So if you have a hypothetical situation where you have infinite such junctions, so infinite such absorbers, still you can only absorb up to like you can only convert up to 67%. So because you'll always have some other losses. So that's the problem. So it's in that sense it's not a very efficient process. You are trying to absorb, you are trying to convert a very like a fraction of your sunlight, but again you can't really beat thermodynamics there. So we are trying to just reach as close as possible to those values.
Yeah, very nice.
Yeah.
And the second naive question is, I mean, you mix all these materials here and you try to achieve, the best result. But are these efforts based on some theoretical simulations, or are they just, by trial and error?
So yeah, so since the beginning of the field, initial many years were mostly trial and error. I would say even now, 60% of what we do is still trial and error because theory can guide you to some extent, but again, they are generally not always applicable exactly when you do the experiment. So experimentally, you always have to find out what works, and that's generally done with some kind of chemical intuition. Let's say it's not randomly choosing something, but with some kind of chemical intuition, you are trying it, but it's not always backed by theory to start with. But what people do is that once something works, then they go back and do some theory and find out why it's work, rather than theory guiding you that okay, I think this should work, go and do it. So it's still not that yet. So yeah, it's still mostly trial and error with some bit of intuition, and our previous experience of last 15 years can tell you to some extent what can work and what cannot work. So yeah.
Okay, thanks a lot.
Yeah, no worries. Thank you.
Thank you, George, for the questions and Chris for the responses. And we still have some time for some additional questions. Okay, I will start with mine and let's see if, in case someone else would like to ask at the end. Chris, again, congratulations on the results. Very interesting and I would say groundbreaking, and not expecting to be honest with you this results with tin, because always tin was the bad guy, but now it seems that it has some let's say interesting properties regarding the ion movement and ion migration. So congratulations on this. You brought some additional and new fresh insights in the literature. My first question is related to this first project, related to the mixed lead tin on the suppression of the ion migration. Have you checked if this behavior is, I mean, thickness dependent, or how much is thickness dependent, and what about compositional dependent? For example, you show, if I'm not mistaken, formamidinium and cesium on the A side, lead, tin, and iodine.
Yes.
What about the composition? Is it sensitive or
it
is general? I mean, if you, instead of cesium, or instead of, mixed formamidinium cesium, let's say we put only Fa or only cesium. What about this? Thank you.
No, the very nice questions. The first question was about thickness dependence. So yeah, we did try different thicknesses, and its behavior is, of course, the trend is the same. Of course, the exact values will be different, but the trend of lower ionic screening for tin is still pretty much constant, even if you thin down them further. So all the perovskite layers for the FETs are close to 200 nanometer thick. You can make them even thinner than that, and I will still expect to see similar behavior. Composition wise, no, that's very important. The reason we chose Fa cesium was because this Fa cesium based compositions generally have lower ion migration. If you have, let's say, pure Ma based composition or an Fa Ma based composition, they generally have more ion migration. So the reason we wanted to start with a composition which is generally not that bad, which is why we chose the Fa cesium. Now, of course, you can say, okay, why did you choose 85%, 15%? It's primarily just coming from what gave us the best efficiency, best mobility. I'm sorry. But again, it doesn't really matter. So in our paper, the supplementary information is pretty long, so you can have a look there. We have shown that different A side. We have also done the A side variation. I'm not just showing it here. A side variation also, and then this also, like if you have a FAMA, the overall trend is still the same. It's just that there will be just more ion migration in both cases. So yeah, that's and the problem is Ma also has Ma, because Ma can rotate pretty easily, so it has a dipolar disorder as well, which kind of also has its own effect when you do the temperature dependent measurements. But ion migration wise, the trend is still similar.
Okay, thanks a lot. And my next question, if there is no other, my next is related to this voltage-dependent photoluminescence experiment that you did, which is very nice. In this case, is it like the material sandwiched between two metallic electrodes? Can you explain a bit the experiment here?
So basically, you take a glass substrate, you deposit two strips of the metal using evaporation, and then I spin coat the film on top. So you pattern this with lithography, the two electrodes, and then I just coat the perovskite everywhere. So perovskite is not only in that one, perovskite is also on top of the electrodes as well. You just form the electrodes using lithography, It's done by some one like my co author in this work, who co-led with me. So he made the substrates, and then I just coated the perovskite layer on top. So it's not only sandwiched between the two; it's everywhere. It's a
Okay,
whole area
but
deposition.
is there any, let's say, possibility that the reactive material somehow interacts because it is in direct contact with
Yeah.
the perovskite?
Yes, it can. So that is what I'm showing here for the tin-based perovskite. As you can see that over time, there is an increase in the PL of the perovskite on the negative electrode. And that's because what we think is because in the negative electrons, you have a lot of electrons. These can actually reduce the tin 4 plus in the perovskite, and therefore the overall PL increases. So yeah, therefore definitely, there can be some electrochemical reaction that can happen on the electrode because it's directly touching the perovskite. For the lead-based case, at least here, because our electrodes were chromium and chrome gold, so these are known to be much stable chemically. That's why we use chrome gold. Chrome gold is known to be a more stable electrode, in chemically, let's say, inert, as compared to others like aluminum or silver. So in that sense, chemically, we didn't really see any significant reaction, but of course, electrochemically, it can still happen.
Okay, thank you. And my final one,
Yeah,
I saw when you presented, I think, the third part of the presentation,
yeah,
you mentioned that you did some solar cells in the EES paper, I think.
yes,
And intentionally, you didn't put any passivation,
yes,
correct? What?
yes,
Okay.
yes.
So, but I mean, in general, for high efficiency, you want to have a passivation either in bulk or on the surface. So, do you expect that in case of passivation, this might negatively or positively affect the the suppression of this ion migration?
Yes, so that's the reason I didn't really use any passivation. So it's known in the literature that if you use any passivation in the bulk or the surface, they can have their own effect on passivation,
Mm.
sorry, on ion migration. So I did not want to have any such like, let's say, combined behavior from the passivation and the tin. So I wanted to just specifically look at the tin, and hence I did not use any passivation. But of course, if you had some more passivation, maybe the process is even more suppressed. But then it's hard to distinguish what is and what is not due to
But
tin.
is there a risk that, for example, with a certain passivation that gives high efficiency, it can somehow increase the ion movement, or it's not the case?
It's a very good question. Um, this is something that we have not looked too much in detail just yet. But I think it's an interesting question to answer.
Because I mean, there are so many passivation materials. Most of
Yes.
them seem to work, but no one reports anything about ion
Yeah.
movement.
Yeah. So it is entirely possible that some of these additives actually um, can suppress or may make it worse. So
Mm.
it can happen both ways. I think there has to be a bit more systematic studies on that. I currently can't answer
Okay.
that very deterministically, let's say.
Okay, and a really quick one. I saw you
Yeah.
had 10% of tin fluoride. Is it
Yes.
because, as a maximum, I mean,
Yeah.
you had a variation of concentrations? Is it because the 10% gives the best efficiency that you stop at 10%? Why, for example, you didn't go for 15% to see if
So
even
it's been,
making the
yes.
halide segregation even more suppressed?
So yeah, so the thing is, the tin fluoride is added to basically suppress the formation of tin vacancies. And so tin vacancies give rise to hole doping. So if you don't use any tin fluoride, the material will be extremely p-doped. If you use some tin fluoride, they will reduce the doping. Now, beyond a certain threshold, this reduction is not much more significant. Let's say you go from 10% to 20%, the reduction is not significant. Secondly, it's been reported in the literature that if you use too much of tin fluoride, the tin fluoride itself tend to segregate, and then they form some other kinds of defects, which are not good. Which is why generally in the field these days, 10% is kind of the maximum that people use for solar cells. Of course, you can use lower, and depends also on the exact process you are following. Sometimes you can just use 5% and it works, or 1% also it can work. But beyond 10%, I don't really see any activity these days because of these issues, as I said.
Okay, thanks a lot, Chris.
Yeah.
Then let me see if there is any additional question, either in the chat. No, I don't see a hand raised. So, yeah, I think it's the time that we conclude this presentation. And before we finish, once again, I would like to thank Chris, Dr. Chrisanu Day, for the availability and for sharing with us your amazing results, and congratulations on them. It was our honor to have you today with us in the Athena Talks. And before we close, next week, we continue on the perovskite, let's say, madness research direction, and we will have Dr. Athanasia Kostopoulou from ISL 4th, and she will talk to us about perovskite-based materials, but now applied on gas sensing devices for sensitivity, stability, and selectivity aspects. So until next week, thanks a lot, and see you soon. Bye bye.
Bye bye. Bye.
Bye.